As we can see, there are quite a few materials terms that are used when describing the properties of materials. In this lesson, we are going to define the terms. It turns out that many of the terms are related to the stress-strain curve of a material. Hi, I'm Christoper Cariazo. I'm going to discuss what is compressive, shear, and torsional deformations and their differences. And let's have an example later. So let's define compression. Compression pushes or presses an object so as to make it shorter and thicker. Let's have an example. Let's say you are sitting or standing. Certain structures in your body experiencing compressive load. So let's focus on this illustration. When you stand, gravity is pushing down on your body while the reaction force on the floor is pushing up. So that's what compression is. On the other hand, tension is the opposite of compression. Tension occurs when two forces pull an object in opposite directions so as it stretches and make it longer and thinner. Example of tension is when you hang on a pull-up bar, gravity pulls down on your body which causes tension in the spine. To solve a tension or compressive stress problems, the formula is force on a member divided by the area. So the answer will have a unit of Newton per millimeter square or megapascal. Now, let's discuss shear. Shear stress is two forces acting parallel to each other but in opposite directions so that one part of the object is moved or displaced relative to another part. The best way to visualize shear is to think of how scissors work. Shear causes two objects slides to one another. To solve the shear stress is equal to V over A, where V is the resultant of shear force and A is the area. Lastly, torsion. Torsion is when forces acting on a structure on a twist about its longitudinal axis. For example, this is what happens in your spine when you twist your body from side to side. So this is the formula in solving torsion. T over J is equal to G times theta over L, where T is equal to torque, J is the polar moment of inertia, G is the shear modulus, and L is the length of shaft. So now we know what is compressive, shear, and torsional deformations. Now we will have an example of those. Example 1. Find the stresses in members BC, BD, and CF for the truss shown in figure below. Indicate the tension or compression. The cross-sectional area of each member is 1,600 millimeters square. So now, let's find first the force in member BD. So, summation of moment C is equal to 0. So, 3 times 4 over 5 BD equals 3 times 16. So, the force in member BD is equal to 75 kilonewton, and it is tension. So now we can solve the stress in member BD. So BD is equal to stress of member BD times area. So substitute 75 times 1000 equals the stress in BD times 1600, the area. So the stress in BD is 46.875 megapascal, and it is tension. For member CF, summation of moment C equals 0. Oh, sorry. Moment of D. 4 times 1 over square root of 2 in CF equals 4 times 90 plus 7 times 60. CF is equal to the stress. CF is equal to 195 times square root of 2. So CF is equal to 275.77 kilonewton, and it is compression. So now we can solve the stress in CF. So the formula is CF is equal to stress in CF times the area. So our CF is 275.77 kilonewton. Times 100 equals the stress in CF times 1600. So the stress in CF is equal to 172.35 172.135 megapascal. The stress in CF is equal to 172.357 megapascal. So, and it is compression. At member BC, so summation of moment D is equal to 0. For BC equals 7 times 60. So BC is equal to 105 kilonewton, and it is compression. Then we can now solve this stress. BC is equal to stress in BC times A. 105 times 1000 equals to stress in BC times 1600. So the stress in member BC is equal to 65.625 megapascal, and it is compression. So that is how to solve the problem in compression. Example number 2 in solving shear stress. As in the figure below, a hole is to be punched out of a plate having a shearing strength of 40 kSI. The compressive stress in the punch is limited to 50 kSI. Compute the maximum thickness of the plate in which a hole 2.5 inches in diameter can be punched. If the plate is 0.25 inch thick, determine the diameter of the smallest hole that can be punched. So let's find first the force. So solution. So let's find first the force. So A So the problem asking the maximum thickness of plate. So let's find first the force. So P is equal to force times A. So equals 50 times 1/4 pi times 2.5 square. Then equals to 50 times 1/4 times 2.5 is equal to 25/16 pi. So equals 50 times 25/16 pi is equal to 78.125 pi kilopound force. So we have now P. So the formula is V equals to TA derived from where V is equal to P. 78.125 pi equals 40 and times pi times 2.5 T. So 78.125 pi equals 40 times 2.5 is equal to 100 pi t. So we now solve for t. T is equal to 78.125 pi over 100 pi. So t is equal to 0.781 inch. Now let's solve letter B. The problem asking the diameter of the smallest hole. So to find the diameter, we use the P equals A equals 50 times 1/4 pi d square. So equals 12.5 pi d square. So we now have the value of P. So using the formula V equals P times A, where V is equal to P. So substitute the value 12.5 pi d square equals 40 times pi d times 0.25. So 12.5 pi d square equals, so 40 times 0.25 is 10 pi d. So our d is equal to 0.8 inch. So that's the diameter of the smallest hole. So let's have an example number 3. What must be the length of a 5 mm diameter aluminum wine so that it can be twisted through one complete revolution without exceeding a shear of 42 Newton per millimeter square? So let's solve example number 3. So our given are our diameter is 5 millimeter. Then our angle is 360 degrees or equals to 6.283 rad. So next is our shear force. Our shear force is 42 Newton per millimeter square. Shear modulus is equal to 27 times 10 raised to 3 Newton per millimeter square. So the problem is asking the length of aluminum wine. So the required is length. So the formula is T over J equals to G theta over L. So first, we need to solve J. So T is equal to pi over 16 times our shear force times d raised to 3. So T is equal to pi over 16 times 42 times 5 raised to 3. So T is equal to 1030.3125 Newton per millimeter square. So let's solve. Then let's solve J. J is equal to pi over 32 times d raised to 4. So substitute pi over 32 times 5 raised to 4. So our J is 6,111.328 millimeter square. So now we can solve the length. So manipulate the formula. So length is equal to G theta over T times J. So substitute the values. Our shear modulus is 27 times 10 raised to 3 Newton per millimeter square times our angle 6.283 rad. Then our J is 61.328 over 1030.3125. So our length is 10.97 millimeter.